Hi. Today we're going to start talking about the gas laws. Okay. Now, the gas laws are basically laws that describe the physical behavior of gases. Now, all gases under normal conditions will react or behave, exactly the same way. All right. This is pretty weird. All right. Solids don't do this, and liquids don't do this, but gases, for reasons that you'll learn once we get into the kinetic molecular theory, gases all behave the same way under the same conditions. The gas laws are basically mathematical formulas and expressions that describe how gases behave under those conditions. Now, the conditions that we're going to be looking at, all right, there's four of them. There's four conditions that affect gases, and these will end up being the variables in the gas laws. Now, first of all, we have P for pressure. All right, that is the pressure exerted by gas particles as they're flying around, and if it's in a container, that's the pressure that they exert when they hit the inside of the container. Okay, that's what causes gas pressure or air pressure. All right, so physical collisions. We also have, remember that they are measured in many different types of units: atmospheres, millimeters of mercury, torr, kilopascals are the main ones, but also, pounds per square inch, for example. There's many different units that you can use to measure them, and you will need to know how to convert between one type of unit and another. Now, we also have temperature. Now, temperature of gas particles, this represents basically the the average kinetic energy of the particles. How fast are the particles moving? Okay. And if you think about it, obviously, if they're moving faster, they're going to increase the pressure, things like that. So temperature is going to be very important. Now, when we talk about temperature, we're going to be talking about absolute temperature. In other words, based upon the Kelvin scale. All right, no negatives in the Kelvin scale. 0 Kelvin, absolute zero, the lowest temperature that anything can achieve. So by using this, by using the temperature always in kelvins, it makes all of the math work out. So we have to make sure whenever we do any of these problems, if there's temperature involved, temperature must be converted to kelvins. Remember, by adding 273 to degrees Celsius. Now, V is volume. All right, that's the volume occupied by the gas particles. Remember, the volume can be in either liters or milliliters usually. And don't forget how to convert between the two. For every 1 liter, there are 1,000 milliliters. All right, so if you're going from milliliters to liters, you divide by 1,000. If you're going from liters to milliliters, you multiply by 1,000. It's that simple. And then finally, the last one is N. N represents the amount of gas. Now, this is going to be measured in moles. All right, a mole is basically a certain number of individual particles. It's a large number. It's kind of like a dozen, but it's a much larger number. Don't worry about that. Just make sure you know that N represents the amount or the number of moles of the gas particles. Okay. Now, when going through and solving for gas laws, any gas law problem, there are 3 rules you got to remember. And you got to do them basically in this order. First, you have to make sure that the units match. Now, most of the gas laws involve a certain sample of gas that is at a certain pressure, temperature, or volume. And then you change some of those. You change the volume or change the pressure. And then your question is, well, what does that do to the temperature? Now, if you have an initial, let's say, pressure and a final pressure, the units of both of those, before you do any math, the units of those must be the same. So if the initial conditions, the pressure is, in atmospheres, and the final condition, the pressure units are millimeters of mercury, you can't have that. All right. You got to have either both of them atmospheres or both of them millimeters of mercury. It doesn't matter which one, as long as they're the same. So in that case, you either take the initial conditions and convert them into millimeters of mercury, or you take the final condition and convert that into atmospheres, as long as they are both the same. Okay? So the initial condition units must match the final condition units. Now, when we do the ideal gas law, which is the fourth law that we're going to be learning, that has a particular constant called the universal gas constant that itself has certain units. In that one, there's no initial or final conditions. Instead, the units of all of those variables have to match the units of R. Okay? We'll learn more about that later. Now, the second rule, you already know, temperature must always be in kelvins. And finally, whenever you're doing any of the gas law problems, this is very important. I know you guys may not be used to this, but I am going to require that you take whatever formula you're using and you rearrange it to isolate the unknown while it's still in letter form, before you plug big old numbers into it. It's a lot easier to rearrange a formula that is just letters than one that has a bunch of numbers, and a lot less chance of getting it wrong, okay? So there's going to be a lot of algebra in this, and you're going to be multiplying or dividing, and so you can isolate the unknown. Now remember, the isolated unknown, first of all, must be a numerator. It has to be on top, not a denominator. And it has to be alone, all by itself, on one side of the equation, equal to, and then everything else on the other side. All right? And you must show the rearranged formula while still in letter form in order to earn full credit. This goes on worksheets, obviously, but when you guys do the tests, if you don't show the work properly, you don't show the formula, you're not going to get credit. Okay? You've got to show the formula rearranged in letter form, and then you plug the numbers in. All right? Now, the first law we're going to learn is Boyle's law. Very simple law. It basically states that the pressure of a given sample of gas is inversely related to the volume of that gas at a constant temperature. So it says constant temperature. We don't worry about temperature for these problems. Instead, it's just pressure and volume. And what this is saying is basically, as one increases, the other one decreases. They are inversely proportional. If one is multiplied by 3, the other one is divided by 3. All right? They are inversely proportional to each other. And if you think about it, that kind of makes sense. All right? If you have, let's say, a balloon of gas, and then you take the balloon and you increase the pressure on the balloon. In other words, you squeeze it. What's going to happen to the volume? The volume is going to get smaller. All right? So they are inversely proportional to each other. And the formula for it is P1 times V1 equals P2 times V2. Now the ones indicate the initial condition. So like P1 is the initial pressure, V1 is the initial volume, where the twos are the final conditions. All right? And it's going to be one of those where I give you P1, I give you V1, and then I give you either P2 or V2, and then you got to solve for the other one. All right? So the initial pressure times the initial volume equals the final pressure times the final volume. Now, the next one is Charles's law. And again, all of these are named after, by the way, the first scientists who studied them and figured out the math and the relationship. And since it's gas laws, these are like some of the first things in chemistry to be studied. Charles was a contemporary of Isaac Newton back in the 17th century. So we're talking 1600s, long time ago, okay? One of the first actual scientists. And according to Charles' law, the volume of a gas is directly related to the temperature. All right? And this one you probably know. You increase the temperature of a substance, it's going to increase the volume. You decrease the temperature, make it colder, the volume is going to decrease. And they are directly proportional. And the formula for it is V1 over T1 equals V2 over T2. This time, since they're directly proportional, it's a fraction. All right? So, and again, since we're dealing with temperature, don't forget all temperatures before you plug them into the formula must be converted into kelvins. Now, I have some sample problems to show you for both of these. So make sure you watch the sample problem video for Boyle's and Charles's laws. This reaction, this sample problem is going to be for lesson E2E, gas laws, Boyle's and Charles's law. First, we have a sample problem for using Boyle's law, which is P1 times V1 is equal to P2 times V2. We first of all go through and we list out all of the symbols. We have initial pressure, initial volume, secondary pressure, and secondary volume. Since this is a word problem, we have to go through and figure out which one goes with which. The question reads, in an automobile engine, the gaseous fuel-air mixture enters the cylinder and is compressed by a moving piston before it is ignited. In a certain engine, the initial cylinder volume is 0.725 liters. After the piston moves down, the volume is 0.075 liters. The fuel-air mixture initially has a pressure of 1 atmosphere. Calculate the pressure of the compressed fuel-air mixture, assuming that both temperature and the amount of gas remains constant. So, as we go through and reread, we have 0.725 liters. Since liters is a unit of volume, we're going to put that down as our initial volume. As we read down with volumes written again, that's going to be V2, that's 0.075 liters. The fuel-air mixture initially has a pressure of 1 atmosphere. So the pressure here is 1 atmosphere. And the question is, what is our secondary pressure? Now, first step, after we list out all of our variables, is to make sure all of the units match. That is the key to doing these problems. The units of P1 must match those of P2. The units of V1 must match those of V2. Since the volumes are both in liters, we're good. If one was in milliliters, we would have to convert one or the other. It doesn't matter as long as they both have the same units. And since P1 is in atmospheres, we know the units for P2 are also going to be in atmospheres. Next, using algebra, we are going to take this formula and rearrange it to isolate the unknown, which in this case is P2. Since P2 is currently on top, all we need to do is divide both sides by V2 to isolate it. V2 cancels. P2 is all by itself on one side of the equation. And rewriting it, we have P2 is equal to P1 times V1 over V2. Once we've rearranged it in letter form, we now plug the numbers in. P1 was 1.00 atmospheres. V1 is equal to 0.725 liters. And V2 on the bottom is equal to 0.075 liters. The liters cancel out, leaving us with atmospheres. On my calculator, any number that's on top I multiply. If the number's on the bottom, I divide. So I simply take 1, I'm not going to bother, multiply it by 0.725, so I take 0.725, and divide by 0.075 equals. Now, for significant figures, I look at all the numbers that I enter into the formula. Whichever one has the fewest, that's how many the answer must have. Since this has 3, this has 3, but this only has 2, the answer has to be rounded off to 2 digits. So instead of 9.666, It is simply 9.7. So 9.7 atmospheres is the answer to that question. Now this sample problem is for Charles's law. The question reads, in former times, gas volume was used as a way to measure temperature by using devices called gas thermometers. Consider a gas that has a volume of 0.675 liters at 35 degrees Celsius and 1 atmosphere of pressure. What is the temperature in kelvins of a room where this gas has a volume of 0.35 liters at 1 atmosphere of pressure? Well, first of all, since pressure does not change, that means it is not going to be part of this problem. So I can just cross that out and ignore pressure. So pressure remains constant. Now I go through and I read the question again, this time using the units to indicate what the various variables are. So the first number I come across is 0.675 liters. Liters is a unit of volume, so that tells me that that is V1, 0.675 liters. At 35 degrees Celsius, so that's temperature 1, and that's 35 degrees Celsius. Now I know that all temperatures must be in degrees Celsius. Must be in kelvins. Therefore, I'm right away going to add the 273 to this in order to get the units in Kelvin. So 35 plus 273 gives me 308 Kelvin. And then I keep reading, what is the temperature? So it's asking for T2 in kelvins of a room where this gas has a volume of, and that gives me another volume, 0.535 liters. Now, rule number 1, units must match. Liters and liters match, therefore that's done. Rule number 2, temperatures must be in Kelvin. I've already converted it to Kelvin, so that's done. Rule number 3, I have to take the formula and rearrange it to isolate the unknown while still in letter form. Now the formula with just volume and temperature is Charles's law. V1 over T1 is equal to V2 over T2. Now, in order to isolate T2, or any variable, I have to make sure that it is a numerator and that it is all by itself on one side of the equation. Since T2 is a denominator, my first step is to make it a numerator by cross-multiplying. So that means that T2 times V1 is equal to T1 times V2. Next, I need to isolate it by getting rid of V1. In order to get rid of a variable, I do the opposite of what it is doing to the unknown that I'm looking for. Since V1 is multiplying T2, I want to divide by V1 in order to get rid of it. Those cancel out, leaving T2 all by itself. Of course, what I do to one side, I have to do to the other, so I also divide by V1 on that side. So my formula is T2 is equal to T1 times V2 divided by V1. Now I plug in the numbers over here in their appropriate places. T1 is 308 Kelvin. V2 is 0.535 liters. And V1 is 0.675 liters. Liters both cancel out, leaving me only with Kelvin, and that's going to be the unit of my answer. Now, for the calculations, I go 308 times 0.535 divided by 0.675 equals. Since all these have 3 significant figures, I know my answer needs to be rounded off to 3 significant figures. And the answer becomes 244 Kelvin. And there it is.